So, welcome everyone to this first talk of the second week. So our first speaker is Hariharan Narayanan from TIFR STCS. He'll be talking about large deviations for random hives and the spectrum of the sum of two random matrices. Please go ahead.
So thank you very much for the opportunity to speak here. The work I'm going to talk about is joined with Scott Sheffield. So I'll start with describing what a hive is. So a hive is a triangular array of numbers in which the boundary values are written on the lattice points in such a way that their piecewise linear extension forms a concave function. So here, for example, we have written 0, 40, 70, 90, and 100. And if you look at the piecewise linear extension, you would get a concave function on this line. And in fact, this is equivalent to saying that the successive differences form a monotonically decreasing sequence. So this successive differences on this line, 40, 70, 90, 100, is actually 40, 30, 20, and 10. And this, of course, is a monotonically decreasing sequence. Then on the right side, again, we do the same thing. We have a concave function and look at the restriction to the lattice points. In this is an integral hive. So right now I'm talking about a hive where all the values are integers. We will also talk about real valued hives in this talk. So here again, mu has been taken to be 40, 30, 20, and 10. So from 100, we have added 40, added 30, added 20, and added 10 and got to 200. And mu here is the successive differences on this line, which is 65, 55, 45, and 35. So these are just the boundary values. But a hive is an extension of these boundary values to the interior in a way that all the rhombus inequalities are satisfied. Now, what are the rhombus inequalities? If you take any rhombus like this, X, Y, Z, W written in I guess, anti-clockwise direction, where X and Z are on the long diagonal and Y and W on the short diagonal, then the labels X plus Z have to be less or equal to the sum of the labels Y plus W. So this is a rhombus inequality. And as you see, unless these inequalities are all satisfied, when you take the piecewise linear extension of the values to these interior little triangles. So for example, here this triangle has 70, 125, 100. And we are going to take a piecewise linear extension so that it's flat over here, or a linear function with these boundary values. This is a unique way of doing so. So we do this for every triangle, and what we want is that the resulting surface or the resulting function from this triangle to the reals is a concave function. And this concave function condition will hold only if these rhombus inequalities are all satisfied. So, so what we are saying is that the piecewise linear extension of the integral of the function from the lattice points of this triangle to the integers forms a concave function. So this is equivalent to saying that all the rhombus inequalities are satisfied. So for example, here we are saying that 100 plus 125, that's equal to 90 plus 140. Here we are saying that 70 plus 150 is less or equal to 125 plus 100, and so on for each of these rhombi. So this if these conditions are hold, it is called a hive. Okay, so this is the first concept. This was introduced by Lubson and Tao in the context of representation theory. So I will talk a little bit more about that later. But before that, I want to talk about one construct which we call the discrete Hessian. The discrete Hessian for us is simply for any rhombus. It's a function from the rhombi to the reals, and it is B plus D minus A minus C for a given rhombus. So whether it's in this orientation or this orientation, the only thing is B and D have to be on the long diagonal, and A and C have to be on the short diagonal. So this is called the discrete Hessian for us. And the connection to representation theory of this is that if you take two irreducible representations of GLN, B lambda and B mu, and you tensor them, Then if you decompose them as a direct sum of irreducibles, then you look at the multiplicity of a given irreducible representation. That is called Littlewood-Richardson coefficient. And the number of extensions of a given boundary value problem like this, where you given the boundaries of the hives, but not the interior vertices, and you just fill it, and you ask how many ways can you fill it to get a piecewise linear concave function with interiors on the vertices. And the answer to this question is it's a Littlewood-Richardson coefficient. So this is where representation theory is related to this, and in fact, this is the context in which Knudsen and Tau first came up with these hives, and they proved something called saturation conjecture using this and related construct called honeycombs, which will also come up in our talk today. So these are honeycombs. They are kind of dual objects to hives.
There's a question, Hari.
Yeah.
Just go back to the discrete Hessian just for a moment, please.
You want me to go back to the discrete Hessian?
Yes.
Yeah. Yeah.
It's a map. Okay, it's a map from the set of rhombi to intervals. Okay, and you want these conditions to be satisfied again. This
Not conditions. He's just taking the difference of the entries on the long diagonal, sum of the entries on the long diagonal minus the sum of the entries on the short diagonal.
Okay. What is that? That should be the.
So that's maybe you can explain why you are calling it the discrete Hessian. That is the Hessian.
So yeah. So I mean, in general, if you have a function from R2 to R, its Hessian is going to be a matrix which is a symmetric matrix, right? So there are going to be three real numbers that encode the Hessian. So this particular thing is not it's some kind of mixed derivative. B plus D minus A minus C. It's some kind of mixed derivative of if you had a smooth function. It's not what you normally consider a Hessian. But these three numbers, these three mixed derivatives together encode the same information that the usual 2 by 2 matrix Hessian would.
Okay, thank you.
Yeah, so I want to now tell you, given a hive like this or a hive like this, how do we get a honeycomb out of it? So the way we're going to get a honeycomb is we're going to look at the gradient of the function on these piecewise linear extension that we said we'll take. That piecewise linear extension is going to have a constant gradient on each elementary equilateral triangle, like this triangle, this triangle. So the gradient is a vector in R2. So we're going to note down all those gradients that are vectors in R2. And note that if I look at the gradient of this triangle on this triangle, and I look at the gradient on this triangle, because the two piecewise linear extensions agree on this line segment, the gradients will have to differ by a vector that is orthogonal to this line, the slope of this line, because on this line the piecewise linear functions agree. Okay, so a little bit of thought will tell you that this is the case, and this is why when we take just the gradients and draw them as vertices, and we join the adjacent triangles, we get a honeycomb like this, where all the angles are 120 degrees. Okay, and these semi-infinite lines correspond to the slopes at these sides. So the position of the semi-infinite line is given by the value of the slope of over here. So and this is a one-to-one correspondence, because if you know the gradients and you know so up to some addition of a constant, the position of these the position of the gradients tells you what the function is, And of course, if you know the function, then you know what the gradients are. So you only know the function up to a constant, but that will not be important for us. There'll be some shift up to which you can fix the hive once you know the honeycomb.
Sorry. So
Yeah.
what is that? What are the symbols next to lambda1 to lambda5 and all that?
These are all, yeah. So this plane is actually, this is in R2, but somehow there's some kind of barycentric coordinates. The asterisks are just there as free variables. You should maybe think of this as a plane where the sum of the coordinates is all constant.
So I should think in R3 where
yeah,
the plane x plus y plus z equals constant or something.
Yeah.
Okay. I see. Okay. Thanks.
Yeah. So, this conference about tropical geometry. So I wanted to mention that these honeycombs do appear, they make an appearance in the context of amoebas of affine algebraic varieties and the spines associated with them. So this is something I know very little about. So I just wanted to mention that there are connections, and which is why I thought this topic was of interest in this conference. And there's also a paper by David Speyer called Horn's problem, Unicurve curve in the Hive cone, where he actually sort of derives honeycombs, the existence of honeycombs, by taking so-called Unicurve curves, which are the zero sets of polynomials of the form determinant of x capital X plus little y capital Y plus little z capital Z equal to 0. So you get certain plane curves, and then there's some kind of tropicalization process which gives rise to honeycombs. So these are somehow the real ovals of a Unicurve curve superposed to form a honeycomb. So this is another connection. And there is also work of Brodsky, Josvig, Morrison, Stonefels, which is in the context of tropical curves in which these honeycombs make a appearance. So this is something I know very little about. I just wanted to show it because these honeycombs do have rich connections to tropical geometry, and wanted to highlight that fact. Let me go back to Littlewood-Richardson coefficients and their connections to other tiling questions. So these these hives, they encode piecewise linear concave functions, but there is a correspondence between those objects and square triangle tilings of certain domains. So these are called mosaics by Kevin Kurbu. So here, as you see, the green rhombi are not part of the mosaic. They're somehow they're what encase the mosaic. But the mosaic itself has squares and triangles, and it's a tiling of a certain domain using squares and equilateral triangles. And here is something called a puzzle due to Knudsen and Tau, which, as you see, there is some resemblance. So it's some kind of distorted version, but it's related. There's some kind of shear transformation involved, perhaps. But this is in terms of rhombi and equilateral triangles, which are labeled 0, 1 in certain ways. But this is perhaps what I want to focus a little more on. So we looked at honeycombs. Now this is actually like a honeycomb. It's a square triangle tiling if in the spaces here you fill them with equilateral triangles, which you can do because these are hexagons. You can tile them using equilateral triangles in a unique way. So if you did that, you would get a square triangle tiling of a certain domain. But as you see, these look a lot like honeycombs, and they are actually dilated honeycombs when you take the lines of the honeycomb and turn them into little thick bands and put squares over them. And these are in one-to-one correspondence with Littlewood-Richardson tableau or LR skew tableau. So these again are gadgets that encode Littlewood-Richardson coefficients. So here what we see is a skew tableau written in some format. The columns are strictly decreasing, the rows are monotonically increasing, and there is one further constraint, which is that when I read this picture from I think right to left and bottom to top, the number of ones encountered at any time is greater or equal to the number of twos encountered at any time is greater or equal to the number of threes encountered at any time, and so on. So for example, here I have 4 ones, then I have 3 twos. I don't have 5 twos, that would not be permissible. I have 3 twos, then I have some ones further, then I have 2 threes, and so on. So these are the LR constraints. So all of these constraints together allow one to represent this picture as this honeycomb. So the ones here have gone to the ones here. This is sort of color coded. This is again from Kevin Bourneau's paper. The twos here go to the twos here. These twos go to these twos, and these twos go to these twos, and so on. So this is actually a honeycomb in some translated language.
So what do you mean?
Yeah.
It's hexagonal tiling of some a convex subset, or what do you mean exactly?
Yeah, so this can be viewed as a square triangle tiling of a domain in which, so this part is all boundary, what you see here. It is not part of the picture. This part is all boundary, it's not part of the picture. This yellow stuff is also part of the boundary, it is not part of the picture. Whatever remains is going to be filled with squares and equilateral triangles. So here only some of the squares and some of the equilateral triangles have been shown, but each of these are actually 120, 120, 120 hexagons, and they can be filled with equilateral triangles in a unique way.
Yeah, but by honeycombs, generally, what do you mean by honeycomb? It's a hexagonal tiling of some domain, a convex subset in R2, or? So
this I would perhaps call an integral honeycomb, but because it's in corresponds to the integral honeycomb. But for the purpose of this talk, I will only be interested in real honeycombs of this kind. So they will all the side lengths should be allowed to be real.
Yeah, and then what is the definition? So it's a tiling of some subset of R2 such that I mean each full dimensional cell is a hexagon, or?
Yeah. So a hexagon in the sense that not a regular hexagon, but the angles are all 120 degrees.
Ah. Okay.
And these semi-infinite lines are fixed in their position.
Yeah. Exactly.
So because these semi-infinite lines are fixed, these vertices also get fixed. This vertex, and this vertex. But that's it. And that corresponds to saying that if I fix the boundary values of this triangle, then the slope of this particular top triangle gets fixed.
Exactly. And this is somehow that honeycomb is somehow dual to this the triangulation, right?
Yes, it is dual. So in fact, if you take this and form a convex surface using by sort of taking a paraboloid on top of it and mapping this subdivision onto the paraboloid in some more or less, then it's a Legendre transformation of the Hive. So you can get there is a way of getting a convex surface out of this, which is a Legendre transformation of the Hive.
Okay. Yeah. This is something we have seen in the past few days. People are familiar with expression of this tropical curve. So we have seen something very similar to this in the past few days. Okay. Yeah. Thank you so much.
Yeah. So there's another. So when in the study of tilings, one method that is used to study the statistical properties of random tilings is to associate a height function to the tiling and then study this height function. So for example, suppose we are interested in square triangle tilings of some domain, what we might do is we would first construct the corresponding Hive, and now that is a real valued function. So studying that is easier than studying the statistics of the different tilings. So this is what one does when one is studying Lozenge tilings of a trapezoid. So here, for example, the Lozenge tilings are in three different orientations: up, down, sideways, and in red, and they're colored in 3 ways: red, green, and orange. And as you see, this gives the appearance of a surface, even though it's just a color-coded tiling. it gives the appearance of a height of a surface, and that appearance of a surface can be translated into giving numbers to all the vertices here, which are height functions. So instead of studying the tiling, one can study the height function and get some statistical information about the tiling. So this is sort of related work that I wanted to highlight. So now I'm going to start moving into the main sort of topic of our talk. So far, I was giving the background and the motivation. So the volume of P, lambda, and mu n. So now instead of calling it lambda, mu, and nu, I'm putting an index n because we are going to basically look at continuous functions on these triangles and have a subdivision by 1 by n on the sides. So the n is for the subdivision length. So the volume of the polytope Pn, lambda, and mu and un, which is the volume of all possible Hive extensions with given boundary conditions of all real Hives, is equal to up to known multiplicative factors involving van der Waals determinants to the probability density of obtaining a Hermitian matrix with spectrum mu n when two independent Hariharan Hermitian matrices with spectrum lambda n and mu n are added. By Hariharan Hermitian matrices, we mean you take for example, in the case of lambda n, you take a diagonal matrix with spectrum lambda n and you conjugate it with a random unitary matrix. Then you similarly take a diagonal matrix with spectrum mu n and you conjugate it with the independent Hermitian independent unitary matrix from the Haar measure. And the first one also is from the Haar measure. So this is what we mean by two independent Hariharan Hermitian matrices. So this is not a very simple operation because you're taking these matrices, their eigenvectors are in some kind of random position, and you're adding these two random Hermitian matrices with fixed spectrum, and then you're able to precisely tell what is the density of the spectrum of the sum. So the exact profile of the spectrum of the sum can be read out from just this work of Knudsen and Tao, from the volume of the polytopes P, lambda, and mu n, or the volumes of these Hive polytopes, basically. This I want to now describe in great detail. So here, what I've done is I've written a Hive in the top corner, and this is what is below is not a Hive. Okay, it's basically, if you know these things, it's somehow derived from a Gelfand-Zeppelin pattern. But let's look at the top first. So in the top, I've started with 0, 15, 20, 15, 0, and then 0, 15, 20, 15, 0. And I filled this in a way that all the parallelograms, which are either squares in this case or parallelograms of this form, satisfy the rhombus inequalities. Now, what we mean by the rhombus inequality is exactly the same thing, except this is now distorted. So we are going to have to account for that. So it's still going to be that the sum of the entries on the non-marked diagonal has to be less or equal to the sum of the entries on the marked diagonal. So here, for example, 0 plus 20 is less or equal to 15 plus 15. And you should think of the marked diagonal as a shorter diagonal and the unmarked diagonal as a longer diagonal. Although from the picture, you can't see that. So, yeah. So what we have above here is an honest Hive. What we have below satisfies all the Hive inequalities except for the Hive inequalities corresponding to the squares. So we don't require that in a square like this, the sum of the entries on the unmarked diagonal is less or equal to sum of the entries in the marked diagonal. So here, for example, 20 plus 7 is greater or equal to 10 plus 15, which violates the corresponding inequality, and that is okay. So below the diagonal, in this thing, we allow for such violations only for the squares. For the parallelograms, they still have to satisfy. Okay, so I'm going to call this an augmented Hive. The part below this is actually more or less just a weighting factor. And in fact, if you fix the values on this pink diagonal, the boundary values of this pink diagonal on the lattice points, then the volume of the set of all ways of extending this to the interior, where the bottom side is set to 0, is simply a van der Waals determinant with 0, 15, 20, 15, 0. So actually it will be the van der Waals determinant corresponding to 15, 5, -5 and -15. So the successive differences. So this polytope, so-called has a volume that is a van der Waals determinant, is easier to understand. This has a polytope which is much more complicated in some sense, and it encodes this random matrix theory question. So are there any questions regarding this? So
what are the red lines over here?
Yeah, so the
Red numbers, yeah.
Red numbers are successive differences between the corresponding black numbers. So 5 is 15, 20 minus 15. 15 is 15 minus 0. -5 is 15 minus 20. I've just written this. So,
Okay.
so
you have highlighted that for some reason?
Yeah, so they form a Gelfand-Setlin pattern. So 15, 5, -5, -15. And then here 10, 5, -5. So
interlacing.
You have interlacing properties. Yeah.
Okay. Thank you. There was some other question.
So go ahead.
Yeah. So in squares and parallelograms below this red line, we assume that that rhombus condition is just satisfied by the parallelograms, like which are not squares, right?
Yeah, not necessarily by the squares. Yeah.
Not necessarily. Okay. Thank you.
So I didn't mention the main thing. So the main thing is, so now suppose I have two matrices with spectrum lambda and mu, and I'm interested in the spectrum of the sum. X, so we call it, let's say, X plus Y, and these are random Hermitian matrices with given spectra. So this picture tells you exactly what the spectrum of the sum should be. And how does that do? How do you do it? So I'm going to say that X has spectrum 15, 5, -5, -15, and Y also has a spectrum 15, 5, -5, -15. Okay, and now what I'm going to do is I'm going to fill this picture with zeros on the bottom row at random, meaning all these inequalities define a polytope. I'm going to pick a random polytope in this random point in this polytope with these boundary values are parameterize the polytope. So it says that I need to fix the boundary values and then I get a polytope. I pick a random point in it and I look at the pink diagonal, just the values on the pink diagonal, 15, 5, -5, -15 in this case. And these numbers have exactly the same distribution as the spectrum of the sum of X and Y. So this is a very miraculous fact, actually, also due to Knudsen and Tau. So the spectrum of the sum of two random matrices is exactly given by the statistics of a random point in this special polytope.
So what about the right boundary?
That is free. It can be anything.
But can you say something about that? And does it mean something in random matrix context?
So the random matrix theory tells you what 15, 5, -5, -15 means.
Yes.
And after that, this is a random Gelfand-Setlin pattern with this starting point.
Yes. No, I understand that. I'm just asking, can you glean something?
There is, because so if you take any, let's fix the spectrum of this for now. So you pick the spectrum of this, and now if you take a random matrix with this spectrum, and you look at the coordinate subspaces of decreasing dimension, then you look at the spectrum of the Hermitian matrix restricted to these coordinate subspaces.
So minus.
Yeah.
Okay. So
then you get exactly these numbers. So this will be the next one, 10, 5, -5, and this will be 7, 0. And so from that, therefore, you can read off therefore you'll be able to read off this as the traces or something of the minors.
I see. Okay. Thanks.
So now what we want to do now is we want to think of this picture as a continuous function from the square to the reals, and then we want to, so where the boundary values in the top on the left are fixed, bottom is fixed to 0, and then let the mesh size tend to 0. And we want to ask what happens. So we get a family of distributions on this pink diagonal, and we want to ask what happens as the spacing tends to 0. So what is the distribution of this thing on the pink diagonal? This is the kind of question people ask in random matrix theory. And we will be looking at this from the angle of large deviations, where what one does is you take one fixed Borel set in, let's say, L infinity 0, 1, and we have this family of measures, and you ask how does the value of the measure, how does so we have a sequence of measures. So Pn is the measure that comes from the nth level subdivision. And we want to know that if I take some element of L infinity 0, 1, what is the measure that this Pn associates with that particular set? So L infinity 0, 1 is now going to be the function that you get by piecewise linear extension on the pink diagonal. So this is some fixed space. We are embedding these family of problems with differing n into this fixed space by piecewise linear extension. And we are asking for a given Borel set in L infinity 0, 1, what does the probabilities that these measures assigned to that Borel set vary according to what law? So this is what this large deviation principle will tell us. So before going into the precise large deviation principle, I need to give you some further notation. So lambda mu are strongly decreasing bounded on 0, 1, integrate to 0. So these are basically the derivatives of these concave functions on the side. Lambda is the derivative of the concave function on this side. Mu is the derivative of the concave function on this side.
Sorry, so just one question about rescaling.
Yeah.
So can you go back to the previous slide? Yeah. So you want to take, so the boundary condition, you want to, after rescaling, set lambda to start and end at 0, and same for mu?
Yeah.
Okay. Yeah, and therefore nu will also start and end at 0.
Yeah.
Okay, and that's why you are able to then map it. I mean, then you're able to consider it in L infinity 0, 1.
Yes.
Yeah. Okay. Thanks.
So lambda n of I is the average of the function lambda on the ith interval from roughly I minus 1 by n to I by n. And mu n of I is the average of the function mu from I minus 1 to n by n to I by n. So sigma of s will be very important for us. This is going to be something called surface tension. It's the negative logarithm of the volume, limiting volumes of certain polytopes appropriately normalized. And S here is the vector of discrete Hessian. So namely, it's going to have 3 numbers, S0, S1, S2. It will correspond to the rhombi of 3 different shapes. Going to roughly mean the average mixed derivative in one direction, second direction, third direction. V lambda is some function of lambda, it's a real number. It is, if this were a summation, then it would be a van der Waals determinant. So it's a kind of continuous analog of a van der Waals determinant. And the rate function, which I will tell you how it plays a role, is given by I of gamma is log of, this is something that has no interactions between lambda, mu and mu. Tau is a linear function, just a fixed linear function. Lambda, mu and nu are varying things which are part of the problem, I guess. And this is an integral over the Hessian, a sigma of the Hessian of the hive. So what we are saying is you take, in some sense, the best hive and you integrate the surface tension of the Hessian of H. Now, H is actually a C0 function, but its Hessian nonetheless can be written on the radon measure, which can be decomposed as the L1 function plus a singular measure. And the L1 part is absolutely continuous with respect to the Lebesgue measure. And this can make sense. So the singular part doesn't play a role in this integral. So this is still something sensible even for C0 functions. Okay, so this is a rate function. This is somehow the important part. The integral of some surface tension of concave functions.
What is d gamma equals nu?
Oh, I'm sorry. So I have written this I in terms of gamma, but gamma is actually this concave function. Nu is its derivative. So just as here we had lambda, and I guess I'm going to say that alpha is the antiderivative of lambda, and alpha is what you see on the boundary. So in this picture, so this here is alpha. The value you see that be alpha. Lambda is 15, 5 minus 5 minus 15. So similarly here, gamma is 15, 5. I'm sorry, gamma is 0, 15, 20, 15, 0. But what I'm calling, so d gamma is equal to something else I had written. D gamma is equal to nu. So nu is the red stuff. 15, 5 minus 5 minus 15.
Yeah. Okay.
Yeah. So d is just a short form for derivative. So this is actually the, yeah, go ahead.
In the last, yeah, you've written, we are integrating it over t, right? So what is t here?
Yeah, t is the triangle of the main triangle that mattered, above the pink diagonal.
Okay, where we consider that rhombus condition is satisfied both over the squares and the parallelograms, which are not squares. Okay.
Yes.
And can you please define this function f again? Like, how is it defined?
So I will define it later because it will require me to introduce other ideas. So I will define it in a little bit. It is a very important part of this talk, but I will define it in a little bit.
Okay, thank you.
Okay, so this is the main theorem. It says that the negative infimum of overall gamma that's in the interior of a Borel set E. So you're fixing a Borel set E in L infinity 0, 1, and this rate is n squared by 2, and an is n squared by 2. If you take the negative infimum over the interior of E of I gamma, that lower bounds the lim inf of an inverse log Pn of E, and the negative infimum over gamma of gamma over the closure of E of I upper bounds the lim sup of an inverse log Pn of E. So as you see, that the gap between this and this is purely that you have the interior of E and the closure of E. So for example, for nice sets E like boxes, it will often be the case that these two will coincide and you will get an equality. So this tells you the exact rate of somehow decay of log of Pn of E when you at a rate function with a rate function of n squared by 2. So I mean, log of Pn of E is going to be a negative number, but it will tend to minus infinity rather fast. So when you rescale it by an inverse, you're going to basically multiply it by 2 by n squared. And after you do that, you actually get something that's bounded by numbers, with independent of n. That's the point here. Okay, so now I'll get to your question of what is sigma. So sigma basically comes from the problem when you have very large hives with periodic Hessians. Okay, and periodic Hessians with average value S0 in one direction, S1 in the other direction, S2 in the third direction. Of so, for example, I'm looking at a hive in the infinite plane, which has a periodic Hessian. Now, because it's infinite plane, it's going to tend to minus infinity as you go farther and farther away. But that is okay for us. I mean, depending on how you look at it, 10 to minus, I think it will have to go 10 to minus infinity as you go farther and further away. But we are asking for the Hessian to be periodic, not that the function is periodic, which is not possible if you have a concave function, but the Hessian be periodic with given average value of S0 on this rhombus, S1 on this rhombus, and S2 on this rhombus. Okay, so now the period is n. So now what I'm going to do is I'm going to take this problem, which seems infinite dimensional or whatever, but now we'll add a convex function with a Hessian of S0, S1, and S2, discrete Hessian of S0 and S1, S2 to this infinite random function, and we're going to get a semi-concave function with upper bounds of S0, S1, S2 on their discrete Hessians, which is now a periodic function. So earlier we didn't have a periodic function, but after you add a concave function, a parabolic concave function, it becomes a periodic function. So we'll make it zero mean to just take away the worrisome shift. We make it zero mean, semi-concave, meaning there's an upper bound on the discrete Hessian, but no lower bound, and require that these are now functions on the fundamental domain, which is the n cross n parallelogram or rhombus. Okay, so now we have a finite problem, and we have a finite polytope defined by all the rhombus inequalities, which are, however, not bounded away from zero as earlier, but they are bounded above by either S0, S1, or S2, depending on their orientation. Okay, so this is some polytope. We're going to call this Pn of S, where S is S0, S1, S2. And the volume of this raised to 1 by n minus 1 in the limit as n tends to infinity is going to be f of s. So this is the definition of f of s. Okay, so the f of s that appeared in the large deviation principle. So basically what this is doing is we are looking at these hives. We are zooming into one particular region of the hive. Now by Alexandrov's theorem, these Lipschitz concave functions are almost everywhere twice differentiable. So if I zoom in on a generic point, I'm going to see something that is like a twice differentiable function. And when I zoom in there, I'm basically looking at what is the entropy of this locally in this twice differentiable place. And I'm getting a handle on that. So that is what this f of s does. It's basically zooming in on a little point of the hive and replacing it by a smooth quadratic and saying, okay, what is the entropy corresponding to it, or what is the measure of the polytope that it contributes to in some sense. Okay, so now I'll speed up because I think I'm going short on time. But basically one has to get control over Pn of s in some analytic way. So we get some lower bound of 1 using convex geometry, and we also get an upper bound of 2e using some convex geometry. So I won't go into the details. And once you get that, then we get that this limit as n tends to infinity Pn of s to the 1 by n squared minus 1, which is f of s, belongs to 1 to e. So it lies inside this interval. And we also get some rates of convergence, which are actually useful in some context for us. But so let me now just tell you some of the tools that go into these sort of large deviation proofs. So a lot of it is actually this Prekopa-Liedler inequality that I flashed through earlier, which says that the consequence of which that we care about is that the marginals of log concave densities is log concave. So if I take a log concave density and I take the push forward of it by a linear map, then the density on the image will also be log concave. That's what's used. And so this is the Brun-Minkowski inequality, which I think many of you may have seen. And the Brun-Minkowski inequality allows us to say that Pn of s is a concave function as a function of s. So Pn of s raised to 1 by n squared minus 1 is the concave function as a function of s. So here is the partitioning trick. So what we wanted to do was we want to somehow say that we want to get a handle on the measure of functions that are close to a given continuum hive or a surface like this. So we want to get both upper bounds and lower bounds on the measure of functions which are within a epsilon neighborhood of a given continuum hive. So what we do for that is we break up the space into these actually I've drawn double layer boundary conditions, but in practice we take 5 or 4 layer boundary conditions. So what happens then is that suppose I take a random hive in this neighborhood of a continuum hive, and suppose I fix the values on these boundary values to whatever I observe in this random hive. And now I ask, what is the distribution conditional on this being fixed to whatever it is of the values in this square and on this square? The point is that their distributions are completely independent. And the reason for that is that I can never have a rhombus that is both having a vertex in this part and having a vertex in this part, because they're just too far away. These bands are 4 to 5 integer lengths away. So you can either have a rhombus that's entirely inside this part, or you can have a rhombus that juts into this boundary, but you can never have a rhombus that both has a part here and a part here. So this effectively decouples the pieces completely. And so the volumes, the conditional on the boundary values being what they are, the volume of the set of all hives, discrete hives with these boundary conditions is just the product of the hives in these pieces, because there is no interaction. Okay, so because we have this product, so now this is how we get a handle on both the upper and lower bound. And I want to say a little bit about the use of Brun-Minkowski. So in order to get an upper bound, now we have some boundary values here and here and here, and we have some values in the interior which are variable. So what we know is that there is, I think, one extension to the interior, because if no extension to the interior, we don't care about these boundary values. So we take that one extension to the interior, we subtract that extension from the polytope in question, which consists of functions with given boundary values and which satisfy all the rhombus inequalities on the interior. So then, having done this, we now get 0 boundary values, because we subtracted the boundary, the extension. 0 boundary values here. Here we get some semi-concave function, but this time, instead of having uniform upper bound of S0, S2, S1, we have some variable upper bounds on the Hessian given by what function we subtracted, because the function that we subtracted need not have been a quadratic function. It could have been some slightly rough function. And in that case, we're going to get upper bounds that depend on that function and which are variable. So we need to show that in this case, the best you could have done in the sense of entropy is if you actually subtracted a quadratic function. So this actually follows from the Brun-Minkowski inequality, together with the fact that you think of these functions with a zero band outside as functions on a torus. So because of the 0 band here, you can think of this not only as a function on a square, but as a function on the torus, because the value here is the same as the value here is equal to 0. And then you kind of rotate the torus and you get a family of polytopes which are rigid body motions of each other. And then you apply the Brun-Minkowski to all of these together. And that, when you do that, you get Qn1 of t lesser or equal to Pn1 of s. This is how we get one-sided upper bound inequality. And to get the lower bound, we have to use something called Fradelizi's theorem. So when you're finding lower bounds, so let's suppose that there is a C3 hive, continuum hive, and we're asking, if I take an epsilon thickness around it, how many discrete hives at a scale of 1 by n exist around it, and we want a lower bound now. What we just talked about was the strategy for giving an upper bound. We need a lower bound now. So to get a lower bound, we basically need to say that somehow the set of functions with these boundary conditions is large. And Fradalisi, so Prokopov-Lindner tells us that if I just look at the set of all concave functions on a square like this, and I restrict the outer band, right? That process corresponds to marginalization in the function space. So, and the marginals of log concave densities, these are convex polytopes, so they're log concave. The marginals of these log concave densities are also log concave by Prokopov-Lindner inequality. So we know that if I just look at the measures on these outer bands, I get some log concave measures. And then this Fradalisi's theorem says that the value of a log concave density at its mean is at least e to the minus n times the density at any other point. This is not true for arbitrary functions, but it is true for log concave functions. So if you use this, then what we get is that somehow the mean of if you look at the value of the boundary values at the mean value, that is actually a fairly likely scenario. So that gives us the lower bound that we require. So I won't go into further details due to lack of time. And I think this is a point also I want to make. So when you're proving lower bounds for large deviation principles, they are the infimum over the interior of E. That's what that's what we are looking at the rate function over. So because it's the interior, you can shift the function by just a little, and you will continue to be in the interior. So if you're a point inside the interior of E, there is always a tiny ball which is also inside interior of E. So you can perturb a little bit. This flexibility is not available to us in the closure, because you can have boundary points and then you may leave the set if you perturb. But this is not true in the interior. So you can actually smooth these hives in the interior when you want to prove the lower bound. And this is what we do. We smooth by convolution. We get a C3 function. And we use what I said about C3 functions to embed a large volume of polytope into the relevant section and get a lower bound. So this was very quick, but running out of time. So let me just mention the other result we have. So this result was about the spectrum of the sum of two random matrices in terms of hives. But it's also of interest to just get large deviation results for hives as themselves, because they're interesting objects, such as piecewise linear concave functions looked at in the large n limit. So can you get large deviations for these functions from T to R? T is the triangle above the pink diagram, and we get some results there as well. But they are somehow less explicit. There's less explicit control in some sense, so they are not as strong, the results we have. And the lower bound and upper bound in general is over different spaces. But if the lambda and mu are C1, then in fact we have a large deviation principle. So if you have lambda and mu C1, then we have a equality in the log volume of boxes, and we also have a large deviation principle if lambda and mu are C1 for the entire function. So what I said earlier was for the pink diagonal alone, which is a function of L infinity 0, 1. But now you can also look at functions in L infinity of T, where T is the entire upper triangle. And there too we get a large deviation principle. And again, the argument to do it for C1 goes through some smoothing, and we have to basically smooth it and yet preserve exactly the boundary value. So there's some care has to be taken. So basically what we do is you're given C1 functions, or rather C2 functions, because we're going to integrate them. C2 functions are the boundary here and here. and we want to get a random C2 hive with a good entropy. We know that there is a random, we know that there is a C0 hive with good entropy, but that is not good enough for our lower bound because, as I had quickly flashed through here, the lower bound involves C2 functions. So it's a restricted class. So this lower bound in principle is lesser, is smaller than what the corresponding upper bound kind of involves. And so basically what one has to do is one has to say that, okay, suppose you give me a C0 function with good entropy or integral of rate function. I will construct for you a C2 function with the same boundary values, which has a good rate function. And this is done by smoothing and patching up in some careful way. So I won't go into further details. I just mentioned that this is one open question, which is how to get rid of the condition of C1, lambda and mu being C1 in this case. So we only have an inequality, but is it possible to get equality here? And then secondly, the open problem is we would like to get a closed form expression for f of s, the limit that normalized volumes of those polytopes involving periodic Hessians, using which we would like to write down a partial differential equation for the scaling limit of a random augmented hive with given boundary conditions along the lines of Cohen-Kenyon prop, a variational principle for domino tilings. Such a result would shed light on tilings, random matrices, and asymptotic representations. This is my last slide. Thank you very much for your attention.
Thank you. Are there any questions?
So did you try making simulations of these large random hives? Like, do they have interesting features like the tilings?
No, I have not actually done this. No. Yeah. I didn't try that. No. Yeah, I think it's an interesting question. There's lots of aspects to it. So Terence Tao had this Java applet on his web page for some time long ago when I think they did this work in 2000. So that allowed one to play around with honeycombs to some extent. But yeah, I think it would be good to do some experimentation because this f of s can in principle be estimated using Monte Carlo. It's the volume of some polytope and yeah.
Thanks.
So for just the probability part of your talk, all these random hives particularly, so has anybody tried to interpret them in terms of tropical geometry? I mean, does it have any meaning? If you add the last part of your talk where you formulated these questions just on hives.
Yeah.
So they give rise to tropical curves, and so what does that mean? Just purely in terms of those hives.
Yeah, so I think the closest to this is this work of David's pair, Vinnikov curve. So he looks at the polynomial little x, determinant of little x capital X plus little y capital Y plus little z capital Z.
Yeah.
And somehow from the plane curves that you get, he constructs a hive using some kind of tropicalization procedure.
Right. Yeah. That seems reasonable, but just the random, the probabilistic part of your talk, all these questions on random hives. So that can that also be interpreted tropically? I mean, yeah.
So X, Y, and Z would then be random Hermitian matrices.
X, Y, and aha. Oh, okay. Aha. And then you think or has Spire himself worked it out that then there is some tropicalization procedure there at that level where X, Y, and Z.
The tropicalization works for any matrix, I think.
Any matrix?
As in Hermitian matrix. So So the randomness is not part of that construction. This paper does not look at random matrices. It looks at the Horn problem, which is simply what spectra are possibly achievable as a sum of spectra of two matrices with given spectra.
Oh, okay. Okay.
So it's an existential question, and that is the question he solves here. There are some remarks he makes, but yeah, I don't think it has been followed up too much. Yeah.
Okay. 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 He does consider Horn's problem, though not with the in the randomized setting.
No.
Okay. Thank you. Thank you so much. Thank you. Yes, please.
Any other questions? So I have a question about your main theorem. So the difference between the lim-inf and the lim-sup for nu, your first main theorem.
Yeah.
So you think this is a technical problem that you could not surmount, or is it just the way things go? I mean,
so I think in general, this is the way things go.
okay. For special classes of E, you would get equality, like what you said, but otherwise, this is the way things are usually formulated.
Yeah.
Okay. Okay. So in some sense, this is the best one can do.
I mean, this is like a standard format of a large deviation principle. This is what people go for in at least in this kind of a setting.
Okay.
This kind of
and it's always in the leftmost and rightmost are always like interior and closure. Yeah. Okay. Okay. Yeah. Thanks. Okay. If there are no more questions, let's thank Hari for a very nice talk. Oh, sorry. I should ask for the online participants. I apologize. Let me see. I'm looking at the online participants. If anyone has a question, please raise your hands. Okay, there are no questions. Oh, yes, there is. Ayush asked something. Let me read out his question. Could you comment on the connection between Lozenge tilings and tropical pseudo-line arrangements and tropical oriented matroids? Work by Ardila and Devlin. Has this been looked into in the case of Hives?
Yeah, so I'm sorry, I don't know this connection. I mean, so the Lozenge tilings are closely related to these, so they are the integer analog of what Arvind was asking, namely these Gelfand-Sedlin patterns. So that I have some idea of, but I don't know what these other things are. I'm sorry. So yeah, I mean they interlace. You have the lozenges. So if you look at this picture that I drew, is from Petrov. So the positions of these green lozenges, they have at every level you have different some places where these green lozenges appear, and those interlace. So like here, this guy interlaces between this guy and this guy. And this guy interlaces between this guy and this guy. You probably couldn't see that. But yeah, they interlace at level. So there's an interlacing system. And these are related to minors of matrices and so on.
Ayush, do you want us to unmute you? AV team, could you unmute? Could you allow participants to unmute themselves? Yeah, Ayush, try again.
Yeah, hi.
Hi.
Hi, yeah, I just wanted to ask another thing about the honeycombs that you considered. So in the work by Joswick, they work with honeycomb polygons. So because initially you had the standard triangle in the initial examples, and then later on, so are you considering like polygons which they define as honeycomb polygons obtained by a family of parallel lines? Like in this case, you can see.
Honeycombs? No, so ours always are this kind.
So dual to like a standard, dual to a Lozenge tiling of a standard triangle, like a dilated triangle.
You do it to a hive in a standard tiling, not
Okay.
Yeah.
Okay.
Yeah.
Thanks a lot.
Welcome.
Any other questions from the online participants? Okay, if not, let's thank Hari for a very nice talk.